I want to give you some history, I guess, tell you about some old work that many people, myself and many other people, were involved with, and some newer work as well. Listening to Agnes's talk, I realized that I haven't done nearly a good enough job specifying who's responsible for what, so please forgive me for not following her great example. Also, I should say this is a kind of odd primary complement to Mark Behrens' talk this morning. I was quite surprised to see a lot of the same ideas coming up there. I guess I want to put this slide up. What is this? What is this? So I'm going to try to explain what this is and where it comes from. But I mean, here are some guesses about what it might be. Could be. These are what are they called? Gliders flying off. Or this is another thing that it reminds me of. But you know, this is a mathematics conference, so we should give some kind of mathematical explanation for these pictures. Well, it's about the atom spectral sequence. Here's another picture. This is the atom's E2 term at the prime 3, a little piece of it. Pretty complicated picture. Many people in this room do very hard computational work trying to understand homotopy groups stem by stem. That's sort of what this is doing. But there's another perspective you can take and try to understand, and that is to understand homotopy groups slope by slope in terms of the atom spectral sequence. So this is related to a chromatic approach. It's not completely equivalent to the chromatic approach. So I'll give you a summary of the way we're going to go. I guess along this column, that's slope infinity. That's the spike that happens here in dimension 0 that accounts for the z in pi 0 of the sphere. And then for a long time, it's been known that this range, this is p equals 3 still. In this range, the answer is 0. That's the best possible answer for a computation, in my opinion. And then there's a range beyond that, between slopes 1/4 and 1/5 that I'll describe to you. And what's new is an attempt, a program, to understand this picture above a slope of a line of slope 1/23, so a significant improvement in getting at some quite complicated parts of this picture. So this is the atom spectral sequence, and like I say, I want you to reset your Wayback Machine to sometime around 1960, when this idea of constructing a spectral sequence by taking the sphere, say, and mapping it to some spectrum, maybe it's a ring spectrum, maybe not, taking the cofiber, iterating that process, and then applying stable homotopy to get an exact couple, or a stable homotopy of that diagram smashed with X, and you get an exact couple, and you get a spectral sequence which is trying to converge to the homotopy of X. So this is this is the atom spectral sequence based on R. R might be a ring spectrum, and in the lucky case, when the self-homology of R is flat over the coefficients, then you get this extra structure. The self-homology becomes a Hopf algebroid, and the E1 term can be expressed as a Kobar construction over that Hopf algebroid. So somehow the beginning of that large resolution is determined by the beginning part. And there's a homological description for E2. And the E2 term is determined by the R homology of X as a comodule over this self-homology. So this is the thing that failed in the work that Mark Behrens was talking about. One place where it certainly succeeds is if the ring spectrum is an Eilenberg-MacLane spectrum for a field. And then this self-homology is the dual Steenrod algebra, and we get this picture that I just had on the screen. This is plotted in the standard way so that S, the homological dimension, is plotted vertically, and the T minus S, or topological dimension, is plotted horizontally. So this is another picture of the atom spectral sequence. I don't remember what the next slide is. Right. Well, at least we know something about this. I'm going to start back. Surely this statement was known well before 1964, that there's a vertical vanishing line beginning at the place where the comodule starts. So if you don't have any X groups in stem degree less than where you have homology in the spectrum. In the sphere, you have that tower generated by a class called V0, say, representing P times the fundamental class. And that acts on the cohomology, on the E2 term for any spectrum. It acts on this cohomology group for any spectrum. And so this is a kind so I want to tell you the first localization theorem, something you can ask, what do you get when you invert the action of that V0 element? And here's the answer to that. So there's two parts to this kind of result. One of them you might call a periodicity result that says that the map from the cohomology to this localization is an isomorphism in some range of dimensions, in some wedge above some line of some slope. And the slope here is 2p minus 2. So for S above the stem degree divided by 2p minus 2, the localization map is an isomorphism. That is to say, everything is periodic, and the periodicity operator is just the vertical operator multiplying by V0. And then there's a localization result that identifies what that localization is. And here the answer is quite simple. You take this comodule over the dual of the Steenrod algebra and pay attention only to the Bachstein operator. That gives you a differential on the module, and you take the homology with respect to that operator. And that is the cohomology. That is the atom's E2 term above that line, after you've tensored with this graded field. So here's the picture. Let's see, I guess I have one more thing to say. Something to notice about this that's interesting is that localized homology depends only on the action of the Bachstein on the module. And another point I want to make, because it's going to, an analog of this is going to come up later, is you can re-express this statement about the homology with respect to the Bachstein in terms of a statement about the cohomology of this exterior algebra generated by the dual of the Bachstein, tau 0 in Milner's terms. Anyway, the cohomology of that exterior algebra, as Mark was describing, is given by the Margulis homology with respect to the Bachstein here. So you can say that the E2 term is given by the cohomology of a much simpler Hopf algebra, just this exterior algebra on tau 0, as long as you stay above that line. You can actually do a lot more in this case. There's a topological theorem that tells you that above that line, some line of slope 1 over 2p minus 2, the entire atom spectral sequence with all the higher differentials is identical with the mod p homology Bachstein spectral sequence. So the whole thing is determined if you know the integral homology. So here's the picture. Above that line, this is slope 1/4 at the prime 3. If you have Z mod 27 in the integral homology of your spectrum and nothing anywhere else nearby, say, then you have these two towers at E2 and a D3 connecting them, because you've got Z mod 3 cubed torsion in the homology. So that's a pretty cool, that's a kind of ideal result that you might like to see in this general framework. All right, well, in particular, if the homology is Bachstein acyclic, that means you get a vanishing line of slope 1 over 2p minus 2. The homology groups vanish, you get 0 for the answer up there. So again, I'm going to look for a way to express what the localization is, what corresponding localization is. So let's see. Let's take the special case where the module is extended from an n, a module over this quotient Hopf algebra where you divide by tau 0, divide the dual Steenrod algebra by tau 0. And I'm going to just say this in an odd prime so that that becomes a quotient Hopf algebra. That's the same thing as, so if n is a comodule over, if the n is the cohomology of a spectrum, this is just looking at the homology of the smash product of the Moore space with the spectrum. And a change of rings theorem shows you that the cohomology of the Steenrod algebra with this coefficients m is isomorphic to the cohomology of the quotient of the Steenrod algebra with coefficients in n. So we should try to understand what happens there. Once you've divided by tau 0, then tau 1 is up next. It becomes a primitive element. It produces an element in the cohomology of this quotient Hopf algebra. That's V1. And V1 acts on any of the cohomology groups we're looking at. And here's the localization theorem that's relevant here, or rather the periodicity theorem that's relevant here, that the map from the cohomology, this is the E2 term for the Moore space smashed with something if you like, to the localization that you get by inverting V1. That's an isomorphism above a line, and now the slope is lower, 1 over p squared minus p minus 1. I think that's a fifth if the prime is 3. So that's a little wedge. I have a picture of it somewhere. But then you'd like to have a localization theorem as well that calculates what that localization is. What do you get when you invert V1 in this X group? So there's actually a formula for this. And to state it, I want to rephrase what that quotient of this dual Steenrod algebra is a little bit. If I divide by the next odd Milnor generator, I get a little Hopf algebra extension. It's a split extension. And so there's a way of saying what a comodule over A mod tau 0 is in terms of the ends of this extension. A comodule over that exterior algebra is just a differential on a graded vector space. The differential has degree, the negative of the degree of tau 1. And the extension provides you with a co-module algebra structure on A mod tau 0 and tau 1. That becomes a differential Hopf algebra. And this is a split extension, so there's an expression for an A mod tau 0 comodule as a differential A mod tau 0 tau 1 comodule. An A mod tau 0 tau 1 comodule in the category of comodules over the exterior algebra. So that's just a different way of looking at it, but in those terms you can say what the localization is, and here's the formula that I was mentioning. So that localized cohomology, localized by inverting V1, is the same thing as a hypercohomology of this differential Hopf algebra with coefficients in the differential comodule over it that we got. So you build the cobar construction, but then remember that there are internal differentials everywhere and build a total complex from that. That's a general formula for the localization that you get by inverting V1. Well, this doesn't look too good because A mod tau 0 and tau 1 is almost as complicated as A mod tau 0. So we don't seem to have made much progress, but that hyper is really important. There's a spectral sequence converging to that, where you first of all take homology of these objects with respect to the differential, and you get a new Hopf algebra. The homology of A mod tau 0 tau 1 is a new Hopf algebra, and the homology of n is a comodule over it. And so I can take the cohomology of that new thing, and that forms the E2 term of a spectral sequence converging to the hypercohomology. Well, the great thing is that the homology of that quotient Hopf algebra, A mod tau 0 tau 1, is really easy to compute. It's basically the same as the calculation that Mark showed us at the prime 2. The operator sends taus to c to the p's, and the homology is just this quotient, this truncated height p polynomial algebra, which is something that we can all compute the cohomology of. So the E2 term in this hyperhomology spectral sequence is typically quite easy to compute. For example, if the module is just the ground field, this tells you what the V-local E2 term for a Moore space is. And it's just the graded field generated by V1 tensored with the cohomology of this little Hopf algebra, the truncated at height p polynomial ring. So there are H's and B's, and I'll say more about where they come from in just a minute. So there's a calculation of the E2 term, and there it is again. And then long ago I showed that in that localized atom spectral sequence, you can compute the differential. You can compute D2 in this spectral sequence approximately modulo some filtration. And the result is there are no higher differentials, and you've computed the V1 local homotopy groups of the Moore space, and you just get the polynomial, the Lorentz series ring, and one additional generator. So you can analyze the atom spectral sequence for a Moore space above a line of slope, well, some slope. That was good, and there's. But let's get back to the sphere now. So here's the picture of the E2 term for the sphere again. And I've called attention to this wedge between slope 1/4 and slope 1/5. So my calculation worked this out for the Moore space, and you just get a polynomial tensor exterior algebra with just a D2 in it. But then much more recently, Michael Andrews worked out the Bachstein spectral sequence that relates that calculation to the actual E2 term for the sphere. And so this provides you with a calculation of the E2 term for the sphere in this wedge above a line of slope 1/p² minus p minus 1. You can see it's quite a complicated gadget. In fact, I'd like to just write down for you what the Bachstein differentials are that he came up with, and just to show you that it's pretty complicated. They're arbitrarily long Bachstein differentials, so you've got long V0 towers up there in that range. It's quite a beautiful picture. This is the picture for the prime 3. Here's the picture for the prime 7, where the relevant slope is 1/49th. So he computed the E2 term for the sphere at the prime 7 above this red line. Kind of amazing. He was also able to compute the atom's differentials above this line, or above a line slightly above it. Is it 41? See, Doug is the guy who does all the calculations in this world. It's just always been that way. I guess you have to subtract something from 49 to get down to 41. All right, thank you. Still, it's impressive, don't you agree? Okay. It's more impressive than this looks because the horizontal scale goes out to 6,000 here, and the vertical scale goes up to 500. So there's compression here. Right. So he calculates the differentials in this part of the atom spectral sequence as well, and sees that there are arbitrarily long atoms differentials up there. I could be wrong, but as far as I know, this is the first verification that there are differentials of arbitrarily long length in the atom spectral sequence for a sphere. So, of course, there's still a mystery about what happens down here. It gets pretty dark, and so we want to try to shed some light on that as well. So the way forward is to think about an observation that Novikov made a very long time ago, that the Steenrod algebra and its dual have this extra grading at an odd prime in which you just give each tau n weight 1. And then the Miller diagonal respects that extra grading. So Novikov noticed and made a big thing about the fact that that tells you that the extension spectral sequence, where I have the reduced powers, the even part of the Steenrod algebra, and then the dual Steenrod algebra, and then this exterior quotient Hopf algebra, this extension spectral sequence collapses, and it collapses in the strongest possible way. E2, that is the cohomology of P with coefficients in the cohomology of this exterior algebra, is isomorphic as an algebra with all structure to the cohomology of A. So this gives you a different way of looking at the cohomology of the Steenrod algebra. It's really the cohomology just of the reduced powers, but with some twisted coefficients. So it's possible to make a lot of progress with that idea. He thought that this was going to be a model for the Adams-Novikov spectral sequence based on BP, and therefore that should collapse as well. So his crystal ball was a little bit cloudy in places, but this is a really good idea. So it tells you that the cohomology of the Steenrod algebra actually splits as a direct sum of the cohomology of these various subgroups. Qn means the part of Q of weight n in the V's. Okay, so that focuses our attention on the cohomology of the reduced powers as a replacement for the cohomology of the Steenrod algebra. So let's think about that for a minute. So now I'll take a comodule over the reduced powers, the dual reduced powers. Now, again, old results show that there's a vanishing line, and its slope is 1/41st? What is? Okay, thank you. But I think it's 1/5 at the prime 3. Thank you, Doug. I was waiting for that. So this vanishing line is the analog for the reduced powers of the vertical vanishing line over the Steenrod algebra that we were talking about before. This vanishing line is valid for any bounded below comodule. And there's an operator that acts along that vanishing line, which is analogous to the V0 operator that we started off talking about, acting along that universal vanishing line. It's generated by the bottom dimensional primitive element in the dual reduced powers. That produces an element in H1 called H. Of course, we're looking at an odd prime, and this is an odd dimensional element, so H squared is 0. That's not going to be interesting if it can't be non-nilpotent, but it has a transpotence class, as it's called, as Cartan called it, in dimension 2, and p times the internal degree, and that is non-nilpotent. And it's really the analog of V0 squared, if I can continue to use that analogy. So inverting B is really completely analogous in this new framework to inverting V0 in the working over the full Steenrod algebra. After all, the dual reduced powers in an odd prime look exactly like the full dual Steenrod algebra at the prime 2, right? So this new operator, B, it acts along the vanishing edge, and we should ask what happens when you invert it. I should say something about B that's not in these slides. The cohomology of the reduced powers is one factor in this decomposition of the cohomology of the Steenrod algebra. It's when n is equal to 0. So the cohomology of the reduced powers is a direct summand in the cohomology of A. And this element B survives in the atom spectral sequence to beta 1, the first element not in the image of J, in dimension 10 at the prime 3. Of course, it's nilpotent in homotopy, so there's an Adams differential that kills some power of it. But it's not nilpotent in motivic homotopy theory, for example, and so I think localizing by inverting B isn't completely a fool's errand. It's likely to have some kind of impact in motivic homotopy theory as well. Anyway, the same kind of arguments that we used before, the periodicity arguments, show you that the localization map from the cohomology to this localization of it is an isomorphism above a much lower vanishing line. P1 over p cubed minus p minus 1. Doug, is 1/23rd right? Yeah. Thank you. I'm not going to ask what it is for 7. 335 or something. It's really big. That's what I think. All right, so that's the goal, to try to understand the localized cohomology of the reduced powers with various different comodules It's really important that we get non-trivial comodules here. So again, this is just the analog of the very simple calculation that I did at the beginning. Well, so I want to, here it is. That's the mystery diagram. That is the cohomology of the reduced powers at the prime 3. So these tables are pretty inspiring. They demand attention, don't you think? You've got to understand how to directly compute the high homological dimension part of this picture. Sorry?
Are you going to tell us how you got that chart?
I will tell you right now, and also at the end. This is one of Christian Nassau's charts. Yeah, not on his website, but I wrote to him, and 6 hours later, this is what I had in my inbox. So. All right, so I want to describe a joint project with Eva Belmont that I've been working on to approach this kind of question. So this is going to use the stable homotopy theory of comodules, or rather chain complexes of comodules. So this idea of thinking about the stable homotopy theory of modules over the Steenrod algebra, I think this goes back to Harvey Margulis and maybe before. Certainly Harvey's book is a big push in that direction. And John Palmieri has a book where he sets this up very carefully. So in this analogy, the sphere spectrum, the unit for the symmetric monoidal structure, is the ground ring, ground field. The Eilenberg-MacLane spectrum corresponds to the co-algebra itself. This is actually going to be valid for any Hopf algebra. Maybe I should say connective Hopf algebra. The homotopy groups of a spectrum are analogous to, well, the spectrum gets replaced by a chain complex of comodules, and so you should talk about the hypercohomology of the Hopf algebra with those coefficients. And if you have some such object, R, then the R homology of X, well, I take the tensor product of R with M and take the hypercohomology of that. So that's the sort of dictionary that we use to transport ideas. And the first idea to transport, after all, is the atom spectral sequence. So, so here it is again. This is the same slide as I started with, except I put tensors instead of smashes here. But do the same thing. So I can form these cofiber sequences, apply homotopy, that is to say, this hypercohomology, and I get an exact couple, and so I get a spectral sequence that's going to converge to the cohomology of P with coefficients in M. I guess I'm thinking of M as not as a discrete thing, just a comodule over P here. So this is an interesting spectral sequence to look at in general, at this level of generality. There's another spectral sequence, which I think coincides with this one in some cases, the Cartan-Eilenberg extension spectral sequence. But it's only going to be valid in very restricted conditions, like when R is the Hopf kernel of a normal map from P to some other Hopf algebra, and then the E2 term of the extension spectral sequence looks like that. But that's a much more restricted case than what this Margulis-Palmeri atom spectral sequence works in. Well, again, there's big tensor powers. Mark was very accurately describing how evil these things are. So you'd like to get rid of them somehow. And the way to do that is to hope that we have a similar kind of flatness assumption. So suppose that R is a ring spectrum in this category, and that the self-homology is flat over the coefficient ring, which is, I see there's, yeah, right, over the coefficient ring. Well, then that self-homology becomes a Hopf algebroid, and the E1 term in the atom's MPASS is the co-bar construction for this Hopf algebroid. And so we get an expression for E2, not as homological algebra with just the Hopf algebras I started with, like in the Cartan-Eilenberg spectral sequence, but with the self-homology as the Hopf algebra now. So, so we can hope that we're in a situation where the self-homology is flat over the coefficients. We'll try this in the case we're interested in, where the Hopf algebra is the dual reduced powers. The Xi bars are the Hopf conjugates of the Milner's X's. You know, by the way, Milner was no dummy. He you know, he wrote that whole paper at an odd prime, and he had taus and X's in the body of the paper. And then he has a little one-page appendix at the end where he talks about the prime 2. Does he use X's there? No, he uses zetas there. So this confusion about X's at odd primes being different from X's at the prime 2, it's not his fault. Somebody else did this, and I don't know who it was. What? Now we are stuck with it. I know, we're stuck with it. And so zetas get a complete, the virtue is that zetas are opened up to reuse like you were doing. So, but there you go. So here's the idea to try to apply this machinery of the Margulis-Palmeri atom spectral sequence to a ring spectrum. And the ring spectrum that seems appropriate is the one, it's very analogous to what Mark was doing, where you take the pth power of Xi1 and leave the rest of the X's in place. So this is this is the cotensor product over a quotient Hopf algebra of the reduced powers given by Xi1 mod Xi1 to the p. And so it's pretty easy to compute what the R homology of, well, anyway, I can say that the R homology of a module is just the cohomology of that truncated at height p polynomial algebra with coefficients in the module, in M. So it's a pretty simple homology theory. The coefficients are just exterior tensor polynomial. We should try to understand how this works out. Well, so the first thing we want to do is understand the self-homology of this R. And the bad news is that it's never going to be flat because you've got this exterior generator here, basically because the structure of P as a D module is complicated. So, but luckily, we're not really interested in making a computation of a stem-by-stem calculation of the cohomology of P. I just want to know what the B localization of that is. And so let's try inverting B on that ring spectrum. So this is going to a periodic ring spectrum, and I can do that in this stable homotopy category of chain complexes, just the way you invert the bot class or anything else. And so the effect of that is to invert B in the coefficient ring. And now we can try to look at the self-homology of this new spectrum, which is just the local B local cohomology of D with coefficients in P. And unfortunately, you still get something which is not flat over this localization most of the time. But you do get something which is flat over the coefficients when P is 3. And so for that reason, and some other reasons as well, now I'm going to restrict to the case when P is 3. Okay? 3 is an OK prime. So what happens now? So we'll restrict to P equals 3. So H has this by degree 1 and 4, and B has degree 2 and 12. And we want to compute the self. And now we want to compute the self-homology of this thing. We want to compute the B-local homology of this thing. And this is going to be a Hopf algebroid, remember? It's going to be a Hopf algebroid over that coefficient ring. So here's the neat fact that Eva discovered that makes all of this work, namely that self-homology Hopf algebroid is extremely simple. It's just an exterior algebra. It's a Hopf algebra. The left and right units are the same. It's a Hopf algebra. It's an exterior algebra on generators that you can write down very simply. So, that's terrific because we want to compute the cohomology of this, and there's nothing easier to do than compute the cohomology of an exterior algebra. So the result is that this localized Margulis-Palmeri atom spectral sequence is just a polynomial algebra, tensored, I mean, over the coefficient ring. And this is converging to the localization that we want. It's supposed to explain the rings of Saturn. Okay, well here's a picture. Oh, so here's what the atom spectral sequence looks like. It's a good idea to grade, to give cohomological grading where it really belongs, in negative dimensions. So H has dimension -1 and B has dimension -2. And these Wn guys have homological dimension 1, and T minus S here is the total homological dimension, the analog of the stem degree. That's what the atom spectral sequence, the E2 term, looks like. Well, so here's a calculation of what the result is. Here's this polynomial algebra plotted out for you. Along the edge here, I've got multiplication by B. I've drawn W2, W3, W4, and so on. I've actually drawn B times those classes. Those classes would lie along the bottom line here. But if I put them all down there, it would all get jumbled up. So I've multiplied them by B in this picture, just to separate them out. And then there's H times those classes, and so you get all of this nice picture. And B is multiplying up in this direction. Well, this doesn't actually look very much like the rings of Saturn, which have those gaps in it where there are big satellites orbiting there that clean out the gaps. But they're not here. So that says they're differentials in this atom spectral sequence. So, we're not finished working on that, what those differentials are, but we think we know what they are. It seems that, it's extremely likely that, there is a D4 and a D8 in this atom spectral sequence. And the D4 is given by this strange formula. Wn goes to H times W2 squared times Wn minus 1 cubed. Strange formula. And when you do that, and W8 is determined by W4 in a way that I'll actually describe in a minute. So let's execute that differential and see what happens. So here's a picture again of the E2 term of this spectral sequence, the polynomial algebra. And then these little blue lines, they're only length 1 because remember, I'm plotting this as if it's in the true topological atom spectral sequence. So all of the stuff I'm doing now is by way of computing D1s, actually. So they just go up by 1. So the differential sends W3 to a B multiple of W2 to the 5th, which is a dot up here. And so I pull this back by taking appropriate B inverses, and I get down to the target of this differential. And then that propagates, and you get a lot more stuff. So the blue little arrows are the D4 in the spectral sequence, and here's what happens when you get rid of that. And then there is a D8 as well, which is plotted in purple here. And once you've got rid of that, this is the picture you get, and I won't test you. I call upon your credibility to believe that this is accounting for the pattern that I showed you before. Okay, so I think this is what the way this atom spectral sequence works out. I want to give you a stronger conjecture, though, that you know, in this whole story, there's an analogy between the exterior algebra that was dominating the picture that Mark was describing at the prime 2, where the Margulis homology is just the homology of a chain complex, on the one hand. And here, we're looking at the cohomology of D, this truncated at height P polynomial algebra. Now, you can compute that cohomology using Meyer homology. There's a Margulis homology where you take the kernel of an operator. Well, I should say what a comodule over this kind of comodule is. It's just an operator of degree whose pth power is 0. The prime is 3 here, so the cube of this operator is 0. So you can compute the cohomology of D by taking the kernel of D modulo the image of D squared. That gives you one parity, and for the other parity you do it the other way around. That's not very convenient. And you know, there's another problem. One of the things that makes life easier over an exterior algebra is that you've got the Kenneth formula operating for you. It's really hard to appreciate how wonderful the Kenneth formula is, and why it works. It works because the cohomology of the exterior algebra, when you invert the generator, is a graded field. So everything is free over it. in this case, it's not a graded field. It's got this exterior generator, tensor polynomial generator, tensor Lorentz ring. It's not a graded field anymore. So there's a Kunith spectral sequence, but there's not a Kunith isomorphism. And so computing the cohomology of comodules over this is a different matter than it is over an exterior algebra. Anyway, here's the way I think that it comes out. So I just define a comodule over that truncated height p polynomial algebra like this by declaring you have these w's of some dimensions, and the boundary operator is given by this formula. And then I do believe that the localization isomorphism, analogous to something we had before, is just saying the localized cohomology of P is the same as the localized cohomology of D with these twisted coefficients. And a little bit more, you can then, so this fits the data, I should say. For example, one of the things I should have pointed out when I was looking at the rings of Saturn there is that it's H-free. You just have these ladders with H connecting them everywhere. There's no independent lines, B lines. They always are pairs connected by H multiplication. That's not at all clear from the spectral sequence. A lot of those extensions are exotic extensions in the spectral sequence, but it's clear from this expression. So it seems like we can reproduce the whole Margulis-Palmeri atom spectral sequence by giving a filtration on this comodule and just giving each W degree 1, filtration 1. And then there's a D4, which you can compute easily, and there's a D8, which you can compute easily, and this reproduces the atom spectral sequence conjecturally. Okay, so that's where we stand. That's the end of my talk, but I wanted to make some acknowledgments. First of all, Doug asked where these tables came from. Christian Nassau's tables that have been around for 20 years, they're still an invaluable source of data to try to understand. And as I discovered, he's very responsive to requests. And Hood Chatham has a new package on CTAN that I encourage you to use to create pretty pictures of atom spectral sequences in general. Also, independent thing, I want to point out a new journal to you. So the Tunisian Journal of Mathematics, new thing on the block for topology editors. It's a general interest mathematics journal published by the same group that publishes AGT and geometry and topology. So if you have some good topology papers, send it to us. We promise a quick turnaround. And well, there is a birthday boy in the house, and so I just want to say happy birthday, Paul. Questions?
How do you compute your D4 and D8 differentials?
Well, that's the question. I mean,
Well, why do you think those are there? Did they make the answer right? Or do you have
that is the reason we think they're there. It also, you can do some of them directly. You can say what, you want to say something, Eva?
Yeah, I can say a little bit more. Like, I don't actually have the D48 thing. These are about you can compare to, I guess, instead of using R, you can use a different thing there. And that will make these different. And I'm like slightly still stuck on like connecting that combination back.
Gotcha. You got another related way to receive it.
Yeah, I mean,
Surely there's another question.
Coffee time.